Hello everyone. Today we are going to see solid state. This chapter will give you free marks. What is meant by free marks? Free marks are nothing but it's just more of the what you have understood. So by seeing the question you can easily tick the answers. That's what I meant by free marks. Let's get started with the free marks chapter. Before getting into the chapter, I would like to let you know solid state is not there in JEE Main and NEET, but it is still there in other entrance examinations as well. So students who were aiming for other entrance examinations or competitive exams, please take care of this free marks chapter and excel your exams. Okay, and also if you want organic purification and qualitative and quantitative analysis chapter also, please tell me in comments or let me know in Instagram page as well. Okay, let's get started. What is solid state? It is about knowing how the solid materials are arranged. Correct. So solid materials can be of crystalline and amorphous. What is that? Let's say I'm taking a NaCl, common salt particle. How does it look like? It is a perfectly crystalline solid. If I'm taking glass, if I'm taking plastic, it is not crystalline, isn't it? So what is the difference between these two? Based on the arrangement of the particles, the solids are classified into crystalline and amorphous. What are those arrangements? Crystallines are orderly arranged like this. But in case of amorphous, it's randomly arranged. It's not regular at all. It's randomly arranged. Due to that, what will happen? A crystalline will have long range order and anisotropic. What is anisotropic? It is different from different directions. The properties are different from different directions. But in case of amorphous, the properties are same in all directions. And since that is orderly arranged, crystalline have its sharp melting point. But amorphous are having range of melting points. It's depend on how it is arranged. We can't say how perfectly it is arranged, right? So we can't say the perfect or the sharp melting point for the amorphous solid. So these are the important properties of these type of solids. The second classification is based on binding of the constituent atoms or ions or crystals. The first classification is ionic solids. Then metallic solids, covalent and molecular solids. What are the properties of these type of solids? Ionic, as we know, ions, positive and negative. So the constituent particles are positive and negative ions. We'll see the examples later. Let me know the properties first. Then metallic solids. How the metallic bonds are formed? It's formed by the sea of electrons. The metals are immersed in the sea of electrons. So this will have positive ions in the sea of electron. Then covalent, which means sharing of electrons, so atoms are arranged. Molecular solids, the constituent particles are molecules. What binds it? Ionic solids means electrostatic force or ionic force. And metallic, electrostatic attraction between cations and sea of electrons. This is strong covalent bond. And molecular solids, weak van der Waals forces and dipole-dipole interactions. This can be asked as a question. So please make a note of it. Then hardness, we know that very well. Ionic are hard. Then metallic are hard to very hard. Think about the iron rod. And covalent are very hard except the graphite. Graphite is a soft one. Think about the pencil. And since the weak van der Waals forces are there in the molecular solids, they are very soft. Brittleness is high for ionic, very low for metals, and medium for covalent molecular, that is having low brittleness. Melting point, moderate to very high, then comes low to very high. Covalent are very high melting points, but molecular solids are low melting points. Electrical conductivity. Ionic are conductors in its molten state. Ma'am, why did you put ions are there? Why did you put that as a bad conductor? Let me remind you one thing. They become ion when it is in molten state or in the aqueous state. Okay, ionic solids are bad conductor in its solid form. Okay, and what about metals? They are very good conductors because they are having sea of electrons. So while the question is about conductivity, just think about two things: whether the free electrons are there or free ions are there. These two are the only responsible for conduction of electricity. Then comes for covalent. They are bad conductors. They won't be forming ions or electrons. And once again, molecular solids, they are bad conductors. But graphite is a good conductor among the solid covalent solids. Why? Because graphite is having free electrons in it. This is an important question. Why solid diamond is not conducting electricity, but graphite is conducting electricity? Why? Because of the free delocalized electron. Then solubility. They are soluble in polar, insoluble in non-polar solvents. But in case of metallic solids, they are insoluble in polar and non-polar solvents. Covalent solids, they are insoluble in polar, usually soluble in non-polar solvents. Finally, molecular solids, some are soluble in polar and some are soluble in non-polar, and some of them are both. It's so flexible. Examples. If you remember the example, the properties will be cakewalk to you. For ionic solid, think about the examples of ionic bonds. NaCl, ZnS, calcium hydroxide, magnesium chloride. And the metals, think of iron, zinc, copper, nickel. And talking about covalent bonding, covalent solids, all organic solids are covalent. And silica, carbides, nitrides. In case of molecular solids like sugar, CCl4, carbon dioxide, H2O, methane, everything is molecular solids. Then we are moving into the important part of this chapter, that is about the crystal lattice and unit cells. First of all, just understand the term crystal lattice. If you are taking any cube, let's say you are taking a Rubik's cube, how it is arranged? It is arranged in the way the small cube is having covered with the large, it makes the large cube, right? Similarly, here also it is following a regular arrangement of an infinite set of points, which describes in a three-dimensional arrangement of constituent particles. What I meant, the Rubik's cube, one cube, that is for unit cell. The smallest repeating unit of a space lattice is called our unit cell. It repeats over and over and over again in the three-dimensional space. Okay. While studying about the solid state, remember the Rubik's cube. Okay. How it is arranged, how it is separated, edges. We have the edge piece and the center piece. Correct. So think about that. If you have, please have that in your hand. Let's see about types of unit cells. There are three types of unit cell. Just understand these three types thoroughly Rest of the chapter will be cakewalk to you. Okay, the first type, that is simple cube, which means only the corners. How many corners are there? 8 corners are there. The ions occupy in the corners only. That is a simple cube arrangement. Okay, but in case of face-centered, how many faces are there in the cube? That's why I told you to pick up a Rubik's Cube in your hand. A 3-dimensional Rubik's Cube is available in online also. You can take that. So how many faces are there? 6 faces. Along with the corners, it is having atoms are arranged in a faces as well. Okay, body center. Along with the corners, the body center, the centerpiece of the Rubik's Cube, the middle one, the center one is also there. Okay, center, that is only one. Okay, cool. So, what are the properties of these different unit cells? The position of the particles in case of simple cube, as I told you, only at the corners. And number of atoms per unit cell, or 1, and the coordination number, which becomes 6. And the packing efficiency. Packing efficiency is how much it is packed, how many free spaces are there. So that is 52. And for face center cubic, at the corners and the center of each face. So the number of atoms per unit cell becomes 4, and the coordination number becomes 12. Then packing efficiency is 74. Packing efficiency is, all 3 points are super important. Among these, the last 2 points are very, very important. If they are asking a question about the packing efficiency, just answer it in 30 seconds. Okay. Then body centered cubic, at the corners and body center. So the number of atoms in the unit cell, that is corners 1, body center 1, so total 2. Coordination number becomes 8. Then packing efficiency is 68. So try to understand the order of the packing efficiency, which one is having more, which one is having less. Okay. Then calculation of number of particles in unit cell. Ma'am, you said 1, 6 and 8. How they have been calculated? Each corner contributes is 1/8 per corner. Why is it so? If you are thinking this part, think about how it is arranged. So each part carries 1/8, 1/8 of the atom or ion. Okay, and the face center contribution is 1/2, because it will be arranged like this. So if a face center is there, only the half of that in one cube, another half will be on the another cube. So that's why we are mentioning half. Face center is only half of the wall is fixed over here. And at edge atom contribution, edges, these are edges, that is 1/4. 1/4, and then body center atom contribution, that is 1. So that's why in SC simple cubic 8 are there. So 8 into 1/8, which becomes the calculation of number of particles is 1, and then face center, that is FCC 8 into 1/8 plus How many faces? 6 faces. So 6 into 1 by 2. So total it becomes 1 plus 3, 4. Right? And then for body centered, I told you that is PCC 8 into 1 by 8 plus 1, which makes it 1 plus 1, 2. Okay, simple calculation. Then, unit cell dimensions. These formulas are important. I'll be attaching this PDF in the first comment or in the description. You can download it. Use it as a formula sheet or lecture notes as well. Edge length, let me take it as A. So, the atomic radius for simple cube, that is A by 2. And then for face center cubic, R is equal to A by 2 into root 2, which becomes 0.353 A. And for body center, that is 0.433 A. That is root 3 into A divided by 4. Then Davis lattices, 7 crystal systems. You just have to understand the structures, and according to that you can go about it. We are going to release a tips and tricks to solve the questions, where we will cover the mnemonics and how to answer the questions very quickly. If you want that video, let me know in the comments. We'll make it soon. And also let me know guys who were attempted JEE main in the January attempt, how many marks you scored, or what else the chapter you want to be covered in detail. Let me know in the comments. If our video is useful to you, give me a thumbs up or put it on the comments. Just let me know, is it impactful or useful to you or not. Okay, let's get back to topic very quickly. Close packing in crystals. The interstitial sites in closed packed structures. There are 3 types of voids. Mostly we'll deal about 3 only, but there are 4. What are voids? Voids are the empty spaces. Okay, so while we are arranging the balls, let's take it as a spheres. So while we are arranging the spheres in different way, like AB, AB, ABC, ABC, I mean the pattern. So while we are arranging like that, it will be forming empty spaces in between. So those forming a structure. According to the structure, we segregate it into 4 different voids. The first one is trigonal void, formed at the center of the 3 spheres, and formula to calculate the size, that is R is equal to 0.155 R. Small r is for the radius of the void, and capital R denotes the radius of closely packed spheres. And for tetrahedral void, formed by covering the trigonal voids by spheres in the lower layer. You know about the tetrahedral shape. Right? Then octahedral void, formed at the center of the 6 spheres. The formula is 0.414 R. Okay, and finally the cubic void that we know, and the R is equal to 0.732 R. Okay, so what are these characteristics of these voids? The question can be asked from this part. We are going to solve the questions in the end of the session also. People who know the chapter. Don't need to revise, just get into the questions and solve it. Okay. If the number of closely packed spheres is n, then the number of octahedral voids is equal to n. And tetrahedral voids is into 2. That's it. As simple as that. They'll give you the n value, just multiply it into 2 for asking for the tetrahedral voids and put it as such for octahedral voids. Then, packing systems. There are 3 types of packing system: square closed packing, hexagonal closed packing, and body center cubic. That's why I meant as a patterns. The spheres are the adjacent rows one over another, like this. And hexagonal packings, the spheres of every second row placed in depression between the spheres of the first row, which is like this. And the body center cubic, not the closest system, spheres of the first row slightly open and not in contact. Okay. So let's say the first row is like this, which will be having a gap in between them. Radius ratio and coordination number. Just to understand or memorize this table, I just put it each of these memorizable part in table so that you can easily understand this and memorize this. Radius ratio from 0.155 to 0.225. The coordination number is 3, which follows planar triangular, and the example is P2O3. These are the most asked examples. So, and for 0.225 to 4 and 4, tetrahedral and structure is ZNS and spherulite. Examples are copper chloride, copper bromide and iodide, barium sulfide, mercury sulfide. And 4 and 4 to 0.732, coordination number is 6, octahedral. Sodium chloride comes under this category. And finally 0.732 from cubic void to 1, the body center cubic, cesium chloride type, and CCI, CSI, CSPR and everything comes under this category. Radius ratio is nothing but the radius of cation divided by radius of anion. What is the number you are getting? That number lies between what? That is the question. Okay, these are the important formulas to calculate the packing fraction. Here Z refers for the number of atoms or unit cell. We know that 1 for the simple, and for body center 2, and for face center 4. We calculated it before. Note down these formulas, which are very, very important. And density, relation between density and the edge of the cubic crystals, density rho, which is equal to Z into M divided by A cube into Na. Na refers for Avogadro's number. What is Avogadro number? 6.023 into 10 to the power 23. Then various type of ionic solids. First one is AB type, zinc sulfide type. Sulfide ions form the CPP structure, cubic close packed, and then ions are present in voids. Which ions? Cations. Cations are present in the alternate tetrahedral voids. And the second type is AB type, NaCl. Again, anions occupy the CPP structure and cations occupies the octahedral voids. And in AB type we have CCl also, where it takes the BCC structure, Cl at the corners of the cube and cesium occupies the center of the cube. CSCl is BCC type. Please note it down. NaCl is simple cubic. CCP close packing. And then AB2 fluoride structure where calcium is forming CCP structure and F minus is goes to the tetrahedral voids. Again AB2. I'm telling you for fluoride type. In case of A to B antifluoride structure, just opposite. These anions occupy the CPP and the cations occupy the tetrahedral holes. Just understand AB2 and A2B type. And also number of formula units, CPP is for 4 and BCC 1. Then imperfection in crystals. We talked about crystals and how it is formed and what are the voids are there. The next one is imperfection in crystals. The most asked imperfections are Frenkel and Schottky defect. Schottky defect is the atom or the ion missing from the lattice point. It's giving the vacancy. Let's say I'm having Na plus and Cl minus structures. Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus. So which will be one of those atoms or in the ions are missing from its particular place. So that what will happen? What can happen? The overall system, it creating a vacancy, so the density of the crystal becomes lower, isn't it? So the density becomes lower. But in case of Frenkel defect, it is a hybrid defect from the combination of vacancy and interstitial effect. So interstitial effect is nothing but atom or the ion present in a vacant void or the interstitial site. Either it can present in the position or in the void present over here. In case of Frenkel, it's a combination of both. The atom displaced from its position to the interstitial site. Interstitial site is nothing but between the ions. Okay, the empty space. Here, these are the interstitial sites. Okay, that is Frenkel defect. But overall, if we are considering the electroneutrality will be maintained in case of Frenkel, so it won't affect the density, it won't affect the other properties because the neutrality is maintained. But in case of Schottky, it is missing either the Cl or Na plus, either the cation or anion that is missing. So which makes it is not neutral at all. And the consequences are the density of the crystal will be lower, the size will become lesser, and other properties also get changed. And F centers. F centers comes wherever the electrons are trapped in an anionic vacancy. So that if the concentration of F centers are high, in that case, the colorless crystals are producing colors. Sodium, what we are seeing in the sodium lamp, the color is because of this F center. Okay, so the color question is for F centers. Dislocalization, it's called line defects, or the line is showing a defect, that is dislocalization. And non-stoichiometric effects where become this kind of examples. Fe, instead of whole number, it is having a decimal points. Electrical properties, you know about conductors. What are conductors? It allows the passage of electric current, and semiconductors, they are in between. intermediate conductivity, and the insulators, they do not practically allow the passage of electric current. But in case of semiconductors, we have types. The first one is intrinsic semiconductor, where the electrical conductivity is due to internal disorder without adding any substances. Just because of the internal disorder, the conductivity is produced. And in case of extrinsic semiconductors, it shows the electrical conductivity is due to the externally added impurities. So what happens? Group 15 elements are, the group 14 elements are doped with, are added with the group 15 elements. So what happens? The free electron, number of free electrons will get increases. Due to that, the free electrons of that, the conductivity increases. That is called extrinsic semiconductors. So 14 is doped with 15. That is called N-type semiconductor. If 14 elements are grouped with 13th group elements, the holes are increases. So the conductivity increases. That is called P-type semiconductors. Then magnetic and dielectric properties. The first one is diamagnetic, weakly repelled by the external magnetic field. For example, N2, NaCl, zinc and titanium dioxide. And paramagnetic substances, these are weakly attracted by the external magnetic field. The examples are oxygen, the O2, Cu2 plus, whichever having the unpaired electrons are paramagnetic, paired electrons are diamagnetic. That we know very well. And then comes the ferromagnetic substances. It shows the permanent magnetism even in the absence of external magnetic field. For example, nickel, cobalt, iron. These are magnetic in nature. But in case of antiferromagnetic substances, they have a zero net dipole moment even though they are having the unpaired electrons. For example, manganese oxide. So please make a note of these examples. Ferrimagnetic substances, it possesses very small magnetic behavior even though the large number of unpaired electrons. For example, Fe3O4. Then dielectric properties. The first one is piezoelectric electricity, where the electricity is produced due to the displacement of ions from their orderly arrangement by application of mechanical stress. Quartz is an example of piezoelectricity, piezoelectric property, which is very important. Then pyroelectricity, some piezoelectric crystals when heated to produce a small electric current. And ferroelectricity, which is a certain piezoelectric crystals show the permanent alignment of dipoles even the absence of electric field. Rochelle salt and barium, titanium oxide. And finally, antiferroelectricity. In some crystals, equal number of dipoles are oriented in opposite directions. So the crystals does not possess any dipole moment. Example, lead zirconate. Please remember the formula also. There may be some questions where they are mentioning just a formula. Okay, not the name. Okay. Let's solve some questions. These are some important formulas: spinal structure, reverse spinal, and isomorphism. Everything. Curie temperature. It's a characteristic temperature above which no ferromagnetism is observed. This can be asked as a question. Then cubic is the most symmetrical system, where the triclinic is the most unsymmetrical system. These are the one-liners of the memory-based questions. Polonium is the only metal that crystallizes in simple cubic lattice. and on pressurizing a crystal, its coordination number increases, while on heating the coordination number decreases. And most importantly, one more point I would like to add, AGBR is giving both Schottky and Frenkel defects. Okay, let's solve some questions. The first question is asked in JEE main. Okay, we can expect in this type of questions in other exams as well. The first question is that in a face-centered cubic lattice, atoms A occupy the corner positions and atom B occupy the face-center position. Okay, if one atom of B missing from one of those face-centered positions, the formula of the compound is. So what would be the formula of the compound if that is missing? So how to solve these type of questions? We know that face center, the first thing first, 8 corners are there. So 8 into 1 by 8, which is for one atom. And for, that's for corners. And for face center, 6 faces are there and 1 by 2 is the contribution. So overall, I'll get 3 atoms. Okay, so they are saying B occupies the face center position, is it? So B is missing. In that case, 3 minus 1, it becomes 2 atoms. So the ratio will be 1:2. Correct. So among the given options, A2, B3, A2, B5, A4, B3 and A4, B4. So which one is correct? Think about it. Which is correct? One atom will be more for B. Comparing A, 1 should be more for B. A2, B3. That is the answer to this question. Hope you understood the question and answer. Let's move on to the next question, that is the unit cell of an element of an atomic mass 96 gram per mole has an edge length of 480 picometer. If the density of the element is 8.5 gram per centimeter cube, the type of cubic unit cell is. So just we have to find the C value. Then from that we can find the type of unit cell. We know that rho, which is equal to Z into M. I have given the formula, right? A cube Na. So where Z value we don't know, we are keeping that as Z is equal to rho A cube Na. Let me write it like this. So M. So what is rho value? Density 8.5. A cube, edge length 480 picometers. So I have to convert it to the centimeter because density is given in centimeter. So for that I am writing it as 480 into 10 to the power minus 10. Of this whole cube into Na, Avogadro number, then M value, that is 96. So upon solving this, you will be ended up the Z value as 4. So 4 means which unit cell? We know that is face-centered cubic. Because primitive means 1, body-centered is 2, face-centered is 4. Then, this is a simple question asked in NEET paper. CaCl has body-centered cubic structure. The distance between the two nearest Cs plus ions. So, I have told you where the Cs plus ions are occupied. It is in AB type, where it occupied the centers and the corners. Cs plus ions are at the corners. So corners, which means the nearest two, correct? Which means just you have to tell me the edge. In the question itself they have mentioned where the A is the edge length of the unit cell. So the answer to this question is A. Just to understand the question, answer is very easy. Then this question, the radius of Na plus ion is 95 picometer and that of Cl minus ion is 181 picometer. What is the coordination number of Na plus ion in NaCl crystal? So radius ratio becomes R plus divided by R minus, right? So 95, both are in same units, please be careful with that, by 181. So the radius ratio becomes 0.525. Okay, so which lies in with category? I have given you the table from this point to this point. What is the coordination number? What voids it is taking? And what are those examples? Right? So for example, if that is lies in the 0.4142, 0.732, then the coordination number becomes 6. Right? So this is answer to this question. NaCl. J advanced question, in a cubic close packed structure of a compound AB2, the anions B form a lattice and the cations A occupy only the octahedral voids. The percentage of octahedral voids occupied by the cation is. So for this question, the number of anions is 4 per unit cell, right? Because it goes in the AB2 type. And number of octahedral voids, which is equal to number of anions, which is again becomes 4, isn't it? So in case of cations, that is half the amount, that is 2 per unit cell as per the formula AB2. So the percentage of octahedral void occupied, which is number of cations divided by number of octahedral voids. Number of cations 2, number of octahedral voids, which is as same as the anions, that is 4 into 100, since they have asked the percentage, which gives 50%. Then percentage of the free space in body center cubic unit cell is approximately. Free space, which means except from the packing efficiency. What is the packing efficiency of PCC? That is 68, right? For FCC, that is 74. 68. So 100 minus 68, which is 32. Hope this session was clear. Please let me know what are the chapters you want. We'll do that in the priority basis. Okay. Until then, practice more and more questions. If you need the practice questions of any particular chapter also, please let us know. Practice, practice, practice.